So, in this lecture we would start by talking about the different options you have, like whenever you are trying to assign some expression to a value inside an always block, inside a procedural block. Now, in the examples we have seen so far, we had used the simple operator equal to sign to assign a value to a register type variable, but we will see now that in fact there are two different ways of doing that. Well, we had look only at one of the alternative, there is another alternative. There are actually two different kinds of assignments you can make inside a procedural block. You recall there are two different kinds of procedural block, always which goes on indefinitely, and initial which gets executed only once and used in the test benches. Now, whenever you have a procedural block, say always, say inside always you have a begin, you have an end, you have several statements in between. Now, exactly how are these statements executing, the semantics of that basically is distinguished by the kind of assignment we are making. There are two options, blocking and non-blocking. So, the assignment that we have seen or used in the example so far, we had used the equal to operator, that is the so called blocking assignment. And the other alternative is that instead of equal to, you can give this less than equal to, this is called non-blocking. So, we will see the difference between these two, what is the meaning.
Sir, one more thing I am not clear with is when are the statements executed serially and when are they executed parallel?
Yeah, here, well, like your question is that when are the statements executed serially and when are they executed parallelly. So, actually we are trying to answer that exactly that question. Now means in the blocking assignment statement, one particular statement, well, it will block the execution of the future statements. So, unless the execution of one statement is finished, you cannot start the next.
So, in that case it is sequential.
It is sequential, but non-blocking in a sense it is parallel. We will see that how parallel it is. So, first let us look at the blocking assignment statement type. Okay. Blocking assignment is of course the most commonly used. See, so inside the always block, whenever we write an expression like say f equal to a plus b, this is an example of a blocking assignment. So, the values of a and b are available from somewhere, they are added and the value is assigned to f. Now, this operation can take some time. Now, here for the purpose of simulation you can explicitly specify a delay, or from the point of synthesis this adder will be having some delay. So, this operation will take some time to execute. Now, blocking assignment says that the target of the assignment gets updated, means this f will get its new value before you start executing the next statement in sequence, before the next sequential statement is executed. So, in the blocking assignment there is a strict order of execution which the semantic demands. So, it is called blocking because one statement is blocking the execution of all statement that follows. A statement using blocking assignment blocks the execution of the statements following it. So, as soon as it gets completed, only then the instructions that follow will start. But there is one catch here. It is said that this is the recommended style for modeling combination logic and not for sequential logic, because in a combinational logic whenever you are specifying some expression, some values, often there is some data dependency, like the output of an AND gate feeds the input of an OR gate, like that. So, most logically you will be specifying the values in that particular order, the way it is computed. But if it is a sequential logic, just to understand that whenever you are trying to assign a value to it, we normally do so in synchronism with the clock. Suppose we give an always block with a pause edge, then inside the always block there are 10 statements. So, what does that mean? That that every time there is an edge of the clock, these 10 statements will be executed one after the other? Not really. The semantic says that at the edge of the clock all the statements have to be executed together, right. So, when you are modeling sequential logic, there has to be something else. In the blocking assignment you cannot model that, that means all the assignments are taking place together. But whenever you are modeling sequential logic, you have a clock, you want that all the assignments you are trying to make, they are taking place together simultaneously. And for that purpose you need the non-blocking assignment. Okay. Non-blocking assignment, the only difference is that the operator, instead of equal to you use less than equal to, this symbol. Now first let us look at the semantic, because from the point of view of hardware I can understand, well, this is the edge of the clock, whenever the edge comes these assignments will take place. But with respect to simulation, what is the semantic? Because we often check or we often validate a design by simulating. So, now let us see what it means with respect to simulation. Okay. So, the non-blocking statement, here the assignment will get scheduled for the end of the simulation cycle. See, end of the simulation cycle means, see here what I am meaning to say is that, suppose you have an always block. You have an always block which is triggered by some posage or negage of some variable, which is a clock something. Now, inside the begin end you have several such statements, f assigns something, g assigns something. Okay. Now, this always block, whenever it is executing, so with a simulator, you think from the point of view of the simulator. The simulator will schedule this block for execution whenever there is a posage on the specified variable. So, whenever there is a posage on the variable, we start a so called simulation cycle, sim cycle. So, in one simulation cycle we are supposed to evaluate the value of f, assign it to it, value of g, assign it to it. Now, what the semantic of this non-blocking assignment says, that the assignment is scheduled normally at the end of the sequential block, which means, again let me come to it, that when the simulator tries to handle this block, it evaluates the right hand side of all these statements. There can be others also, h assigned something. It evaluates the right hand side of all of them, but when it reaches the last statement in the always block, only then it assigns the values, right. So, it is quite possible that you have say f appearing in the right hand side of some expression, no problem there, because you are taking the old value for the calculation. The value will get assigned only at the end, after all the statements, all the expressions on the right hand side have been evaluated.
This is actually modeling sequential.
Actually modeling sequential logic, yes. So, this normally occurs at the end of the sequential block, and very naturally the statement subsequent to the instruction which is currently being evaluated is not blocked by the assignment, because if there are 4 assignments, the 4 assignments are they are essentially going on concurrently. There is no dependency between the assignments, all the expressions are evaluated, and at the end of the block they are all assigned together, they are going on in parallel. Okay, fine. And you can understand that very naturally this is the recommended style for modeling sequential logic. Yes. Yes, we will come to that shortly. This is the recommended style for modeling sequential logic, and well, so here as I have said that we are essentially using several rich type variables and you are assigning some values to them synchronously under the control of a common clock. This is the typical usage of these assignments. Okay. So, some rules you need to remember and you need to follow. See, I have repeatedly told this, that the user can specify some delays along with each of the blocks. Now, whenever you are carrying out synthesis, the delays are all ignored. Delays make sense only from the point of view of simulation. Okay? But there is one problem here. Suppose in a code you explicitly specify some delays, #10, #20 something, then you are possibly running into a problem if your final target is to do synthesis, because after synthesis delays will be as per the components you are using, the library, the technology library, and in simulation delays are as per the user specified values. So, when you see and compare the simulation outputs, there may be mismatches, the values may not be changing at the same times. So, you have to remember this when you are doing the simulation or carrying out the simulation. Okay. So, this is what is mentioned here. This may lead to functional mismatch between the model means the specified code, and the synthesized netlist. Design model we are checking through simulation, and synthesized netlist we are obtaining through synthesis, and then again we are simulating. Okay.
So we can never use the delays in an always block.
We can use delays in the always block, but they will be used only for simulation purpose.
So always block is a synthesizable block, and delays we can't synthesize. So how do we
See, so as soon as you include delays, so unless the synthesizer ignores the delays, they will not be synthesizable. The always block will not be synthesizable. But see, synthesizable, you have a subset of Verilog features which are synthesizable. We will be discussing this issue later, that exactly what is synthesizable, what is not. And if you just include delays somewhere, there are some synthesizers which will work very well, they will ignore the delays and go through, but there are some other synthesizers which will give you some error messages while synthesizing. It will say that the always block is not synthesizable. Those error messages are generated from you can say from the prediction that if you are using such delays in the always block, later on your simulation results will not match. So, for that purpose it will give you those messages at the beginning itself. So delays are allowed by some synthesizers, but some do not allow. But you will have to just read and understand exactly what the synthesizers do with the delays, exactly how they deal with it. But from the user's point of view, you just remember one thing: delays are ignored by the synthesizer. They are used or utilized by the simulator. That's all.
So isn't there any standardization of synthesizer, like some of them ignore it, some of them accept?
There is no standardization of synthesizers, unfortunately. The same code which, for example, you will run correctly on Synopsys, you will get a lot of error on Cadence tools. There is no standardization as such.
And even for simulators?
Yes. So that every particular implementation of the synthesizer, they will have a booklet they will give to you that, well, this subset is synthesizable, this is not synthesizable, you follow or restrict to this set, but that set is not universally accepted. Some synthesizers accept something outside which others do not accept.
So then what is to be done in this case? If the delays are not, then we have to put exactly the flip-flops.
Yes, you have to put exactly the flip-flops, yes. Or you do not use the delays, you just use the syntax or and the semantics of the language take care of it. So, if it is for example, non-blocking assignments, you know that all of them will be assigned at the end of the clock, you need not give any delay. And if it is a continuous assignment statement, you give 0 delay, that is a 0 delay simulation we assume.
But in the circuit, I may require some places where I have to give some delay.
Yeah.
Then in that case, I have to give some
That delay you can give globally outside the always block, but inside the always block you need not have to give the delay. With each statement you need not have to give the delay, that is the thing. Okay. Fine. Now, here one of you was asking earlier that if we can mix blocking and non-blocking assignment in the same always block. Yes, we can, but the only restriction is that we cannot use the same variable as the target for both, but we can mix them up. The semantic will be the same. Wherever we are using non-blocking assignments, they will not get blocked by the blocking assignments. They will all be evaluated concurrently and waiting for the clock edge to come at the next simulation cycle. And wherever you have the blocking statements, they will be executed sequentially, but it is not a good practice to do so for obvious reasons. You either use only blocking or only non-blocking in an always block.
One more thing, like in non-blocking assignment, if we have non-blocking assignment in always block, so there we giving delay does not make any sense.
Non-blocking assignment giving delay does not make any sense because it is always triggered by the clock. Yes, true. Okay, so now let us look at some of the examples. This is an example of an up-down counter with synchronous clear. Well, here what we are modeling, we are modeling a counter. This is an 8-bit counter with data in, which is given by D in. The output value we are calling count. Now, in addition we have several other controls. We have a clock, we have a load control, and we have a control mode. This is a counter where all the signals are handled in a synchronous way. That means clear, load, everything, they will be, or count, all will be done in synchronism with the clock. That is how in this Verilog module we have written the code. So, you look at it, input and output, these are 8-bit quantities, output is of H type. Here in the always block, we are triggering by the clock, posage of the clock, clock is a positive edge triggered, and whatever we are doing inside the block, that will take place whenever the clock edge occurs. Now, what we are doing, we are checking if load is 1. If load is 1, this input value is getting loaded in the counter, parallel in. Else, if clear is 1, the counter is cleared. Else, if mode is 1, then it is up count. If mode is 0, it is, sorry, this will be down count, count minus 1, right. And see, here all the assignments are non-blocking assignments. They are all assigning to the same variable, but depending on the values of load, clear and mode, only one of them will be executed. Right?
Practically it doesn't make any difference.
Doesn't make any difference.
But there is already if else.
Doesn't make any difference. So, here all means depending on the if statement, this will be evaluated, whatever value is being evaluated, that will go into the count only at the end of the simulation cycle. Fine. This is one example, and I am giving another example where we are trying to design a general n-bit counter, because sometimes in a design, instead of designing a hardware block of a specified size, it is good to have a general design. In this example, we are showing an n-bit counter, and since it is specified by a variable, it is sometimes called a parameterized design, and having a parameterized design is good idea wherever possible. Here there are 3 input outputs, clear, clock and count, simple. There is no parallel load facility. So, we have only the count value available, count, we have a clock and we have clear. So, this n is a parameter, a constant with a name. So, in this example we have taken to 7, you can change this one line and this will change. So, always at the negate of the clock, clock is negative edge triggered. If clear, count is 0, else count is count plus 1, simple. In this way you can create a parameterized design. So, the purpose of this example is to show, that means how you can make or create a parameterized design. So, it is a good idea to have a parameterized design, but one thing, if you have a parameterized design, then in some cases, of course, in a counter it is simple, in some cases it may be difficult to specify in the structural level. You may have to give the specification slightly at the behavioral level. Okay.
So here else is not concurrent with F now, because if else is itself.
Else is not concurrent, either this or this will be executing, one of them will be executing. There is only one block, in fact, in this always there is a single statement, but there can be multiple statements also. Okay. Now, a few other points, that inside a module you can have more than one clocks. This is perfectly permissible. Well, of course, this example is nothing meaningful, but this shows that you have two different always blocks. One is triggered by clock 1, other is triggered by clock 2. So, actually when this is synthesized, you will be getting a hardware like this. This will be an XOR gate. These will be flip flops. The first flip flop will be clocked using CLK1, second one negative edge will be clocked using CLK2. This will be D input, this will be the Q output, D, Q. So, the synthesizer will be synthesizing this into some hardware like this. So, you can have multiple clocks in this same module, no problem there. Not only that, you can have multiple edges of the same clock. Say this is a similar example, that here it will synthesize like this. You have an AND where the inputs are T and B. This is T and this is B. You have this is an OR, this is A and B. This will be one flip flop, this will be another flip flop, and first one will be generating a value called F, second one will be generating a value called T. So, actually this T will be fed back here, right, and this F will be going out. And regarding clock, this same clock will be triggering this as well as this, but here the edges are different. So, it is a very good practice in high speed design that you try to do some computation at both edges of the clock. Just instead of waiting for the next clock edge, you can do something in the leading edge and something else in the falling edge.
Instead of the two always block both triggered by the same event.
Two always blocks can be triggered by same event, no problem there.
If these statements.
See, there can be two always blocks which can be triggered by the same event. This can be POS clock, this can also be POS clock, but only one thing you should ensure that the left hand side of these blocks should be different.
That's what I'm saying.
Yes, the same values you cannot assign in two different blocks. That will be a conflict. So, the synthesizer will be giving you an error, that is a conflict.
So it is assigned to the same thing. Like
Assigned to the same thing, yes. You are assigning this to F, also this you are assigning to F at the same.
not this to F. Suppose it is T and B is assigned to F, and again T and B is assigned to F. Like I am repeating the statements. Complete statement.
Repeating this statement, well, if the synthesizer is intelligent enough, it can try to optimize that, but otherwise it will give an error. Normally it will give an error.
So if you assign them to same thing,
Huh.
and if the statements are blocking, then also it will be
If you assign to the same thing,
two different expressions to a same thing. Say A or B and A and B.
Huh.
But the statements are both blocking in nature.
Huh.
Then also an error is.
so you have F equal to A and B, and you have F equal. Gotcha. There is one always block here, there will be another always block here. F equal to A or B.
Both always are running concurrently now.
Concurrently, yes.
Then why
See, depending on the event list, well, if the synthesizer can find out that the event lists are not mutually exclusive, then it will give an error, that is conflict. The synthesizer should be able to find out that these event lists are mutually exclusive, then only it is allowed, otherwise it is not allowed, obviously. Okay. Now, let us look at another interesting example.
Sir,
Yes.
here in the it was blocking till the values of A and B were available.
In the earlier case, this one?
No, the example which you used.
Okay.
It is like blocking till the values of A and B are available.
No, blocking means this statement will well, if there are more than one statement in the same block, then only it is blocking. There is only one statement, so it does not matter.
So it will block till what time? Till A and B are their AND is taken and assigned to F till that time.
See, the blocking makes sense if there is more than one statement, unless the first statement finishes, the second cannot start. But here, since there is only one statement, that phenomenon does not occur.
Yeah.
But here this AB will be evaluated and will be evaluated, will be assigned to F.
So the meaning of first statement finishes is like the AND of A and B is taken and assigned to F. Or it has to wait for A and B.
No. That depends on the event list. If the event list triggers, so whatever is the value of A, B, it will take. Okay.
Suppose you are equal to A or B also in that same block. So then it first evaluates F equal to A and B.
Then evaluate F equal to A or
So
B. Yes.
finally it's always F equal to A or B.
That is allowed. Yes.
But so it
always has the same statement, like two blocks always at the same events, then effectively that is the same block.
It is the same block, but if your synthesizer does the optimization, it will find that they are identical, they are redundant, they will remove it. But if it doesn't, there won't be any conflict. In that case.
But if it is running parallelly two different, like if it is not in the linear, then
If it is not in linear, it will give an error that there are two blocks which are not mutually exclusive event list. They are trying to assign to the same variable.
So in this case, like suppose F equal to A and B and F equal to A or B were in the same always block. In hardware, how would it be? The outputs of an AND gate and an OR gate are the same wire.
See, the optimizer again will be just removing the AND gate. There will be a simple OR gate. The last one will remain. That depends on the synthesizer. I don't know how the synthesizer will do. If it does an optimization, it will remove simply it will remove the AND gate and will not consider the delay at all. It will take only the OR gate. Okay. So here we are trying to code a ring counter module. Ring counter, you remember what it is? There is an 8-bit ring counter, there is an 8-bit register where there will be a single 1 and the others are 0. They will be, these bits will be rotating. So, this single 1 will be moving around. It is a left rotate ring counter. This is the one way in which I have coded this. Now, let us inspect and find out if this program is correct or wrong. Clock init count. This output is 8-bit count 8-bit. This is I have declared as reg because it appears on the left hand side. And we are activating this block always at the positive edge. In fact, this consists of a single statement. This says that if init is active at the clock, then you initialize the register with this initial value. Else, we left shift count by 1. See, count the way we have defined, the rightmost bit is 0, leftmost bit is 7. Then we assign count 7 to count 0. Now, tell me, is this a correct way of specifying this one? Both are blocking statements, you recall. First this will be executing, then this.
No, because that value has changed.
In the first line only the 7th bit is lost.
Yeah, so if this was the initial value, for example, the first line will do a simple left shift on this and the value will become all 0. That 1 is lost. So, here whatever you are assigning to count 0 is the current value of count 7, that is 0 now. So, this is a wrong way of specifying this, you cannot do this.
Either you make it non-blocking or move the second statement on the top of the.
Yes, either move the second statement on top, that also you cannot do.
No,
That also you cannot do, because
it has to be non-blocking.
non-blocking, or in some way you have to specify that these two are concurrent.
In non-blocking also, sir, there might be two answers.
Okay, let's see. Let's have a non-blocking solution and let's discuss the solution. This is the same thing. We have changed the blocking assignments to non-blocking. The rest are all same. Now here, do you foresee any problem? Suppose you have this initial value. You are doing these two things. So you are evaluating count shifted by 1. You are using 7 bit of the previous count to store in count 0. This is all right, but you can take this solution with a pinch of salt. You are not sure what the synthesizer will really do.
Yes.
Now in the first statement, you are assigning something to an 8 bit register. In the second statement, you are assigning something to the least significant bit of the same register. So, therefore, how can you do the two things together? What is the idea? So, possibly this is also not the correct solution. Some simulator or synthesizer may give the correct result, some may give wrong result, because in fact this is one example which gives different results for different synthesizers or simulators. Now, a correct solution will be to do the two things concurrently. So, the last solution we are showing here using concatenation operation, we are doing this concurrently. See what you have done. This is your count. This count is an 8 bit register. This is your bit 0, this is your bit 7. You are taking count 6 to 0, you are taking only this much. We are concatenating with this on the right, the whole thing you are assigning it to count. That is really what you want. This is a current description, but it does not contain the shift operator. So, your synthesizer must be intelligent enough to analyze this statement and find out this is actually nothing but a shift register.
Sir, even if it doesn't find out, anyway we are giving the right result.
We are giving the right result. But in terms of hardware, a shift register has a known structure, it is already there in the library perhaps. So, if the synthesizer can find out that it synthesizes to something which is already there in the library, it can simply pick it up from there. So, otherwise it may have to redesign the wheel, use flip flops to implement this, from there it may start. So, the area will be more, delay will be more, because the designs which are there in the library, they are highly optimized. So, that is the advantage. Okay. Fine. Now, inside the always block, you can use loop statements. Now, in Verilog I have mentioned that you can have 4 different kinds of loops. While, just like C, based on some condition you repeat. For, given some condition exactly in C. Forever is an infinite loop, and repeat is a loop which is executed specified number of times.
Sir, why is repeat existing at all if there is a for?
Repeat is more readable, that is why. See, for may be alright for C programmer, someone should not like that I have to write so many things just to specify it, I have to repeat it 10 times. Repeat 10 is much easier to specify. Just like that, repeat can be synthesized with for easily, no problem. So, but these are the 4 statements which are available to the user. Well, now, This issue we shall again deal with later when you talk about the synthesizable and non-synthesizable subsets. Well, it depends on the synthesizers. Some synthesizer supports only for, some synthesizers support for and repeat, but whatever is the case, they will support only loops with constant indices. Just if you write a sorting program with a parameter n and give it to the synthesizer and then if you ask it to synthesize the hardware, it will give an error. You will have to specify how many times the loop is executing exactly, because the way the synthesizer will work is that it will typically unroll the for loop. If the loop is executing 10 times, it will create 10 copies of the body, then it will try to optimize and then synthesize, right, because implementing a loop as such may not be very efficient. Well, you can do in some cases you really need to do that. For example, I am giving you an example. Suppose you are designing the control unit of a computer CPU. There are certain regular operations you need to execute in a loop repeatedly. There at the structural level you can explicitly specify that these are the blocks that need to be repeated, but not using a for loop. You will have to explicitly specify the hardware for that, a counter, checking the comparator, etc. But if you simply specify for loop, it has to be a constant.
So this
In terms of the
many Verilog synthesizers supports only for loop means they don't support the other three things.
They don't support the other. These are fine for simulation, but when you are interested to synthesize into hardware, the synthesizer can run into problem if you use while, for example. Okay, a few other things. Well, in many design you may require some high level blocks like memory. Like you may have a design which contains some logic, it can contain some memory also. Now here there are several options you may explore. Normally the synthesis tools which are existing, which are there commercially, they do not synthesize memory. Well, there can be some memory modules already there in the library, like I can have a 4K, 8K, 100K, 1 meg memory module already there in the library. It can simply pick it up from there. But in my Verilog code, I specify a memory of any arbitrary size. It will automatically generate that memory. That is normally not the case. So synthesis tool, they are not, well, we should say not at all efficient in synthesizing memory. Use memory in your design is to have them available as components in the library, and in your design you can instantiate them as a component. This is the, if it is not there, you will have to make with either what is available, or you can specify it as an array of registers, but that will be highly inefficient in terms of hardware implementation. So you can implement memory as 2-dimensional register file, it will work correctly, but in terms of performance and power consumption it will be very bad, right. So just apart from the case where you need small memory banks, I mean small register banks, there possibly you can just use them as register file, but in the other case you typically use them as components. And I am giving a typical example how you may instantiate that. You can have something like this. Say, well, this is the high level block which can use module. Other than memory, there can be some logic also, but here we are instantiating this ROM component in the design. There can be other statements also. So this is how you will do it. I am not going into the detail of this, fine. And well, like when you are designing say processor or some kind of high level data paths, then in order to reduce the number of driver circuitry drivers or muxes, demuxes, we often need to model tri-state buffers or tri-state gates. There are some explicit ways of modeling tri-state gates. I am giving an example. This is a simple example which models a bus driver in out enable. In fact, this models an array of 8 bus drivers. There are inputs and outputs. These are indexed by the numbers 0, 1, 2 up to 7. These are in 0 and these are out 0, out 7. And you have a control unit called enable. This enable goes into the control of all these. Okay. So, if you specify like this, that if some of the input changes state, either enable or one of the inputs, then, well, if enable is high, means the buffers are enabled, then in goes to out, else you explicitly specify Z here, tri-state. This high impedance state goes to out. So, if there is an explicit assignment like this, then this will be modeled as a tri-state gate. But in continuous assignment, if you drive 2 computations into the same net, by default it will not synthesize as tri-state. Explicitly you will have to specify in this way that you require a tri-state gate out here, then only then it will be synthesized as a tri-state, right. So, this is actually one way you can do that, fine. Okay. So,
here explicitly specifying is just this out is equal to 8 pieces.
yes.
Sir, in case it is not explicitly specified, then it becomes indeterminate.
It becomes indeterminate. It means it becomes indeterminate. Simulator will give some x value in the result, indeterminate value, and possibly during synthesis we will be getting a conflict error.
So if we don't specify else, then it will use a register for out, because it a latch for out.
If you don't specify this, if you don't specify the else part, then this will be a simple latch, yes. Then this will be an 8-bit latch, right.
So it will give the previous values too,
Previous value.
which can be anything.
Because enable, you don't know when enable will be active.
Yes.
So you have to remember the value of
So in that case, it is not a tri-state.
Yeah.
in that case not restricted. You have to explicitly specify that under certain condition the value will become Z. Then only you will be having a tri-state logic family. So we have seen so far that using Verilog language we can model combination logic, we can model some sequential logic also. Now we will see specifically how we can model say FSMs, finite state machines. See, using if then else we can do fine, but normally finite state machines they are specified either using a state diagram or a state table. From there should be a very structured and well defined way of specifying a finite state machine, and if you follow those well defined styles, then it will also be easier for the synthesizer to identify that well the user is actually trying to model an FSM, and let me use the best known method to synthesize it. So there are some design styles which are there. If you follow the design style, it becomes easier for the synthesizer, and it is always good to use those design styles. So you can always give a big array of if then else statements, but that can be a little problematic for the synthesizer to get an optimum realization. So these are the things we will be discussing in detail in the next class, but just let me tell you now that we will be broadly looking at two different kinds of FSM, as you know, Moore and Mealy. Both the examples we will be looking at. Now, if you recall Moore machine, the next state logic, generating the next state, this depends on the present input and the present state, whereas the output logic depends only on the present state. So, a typical example is a counter. Counter, the output value does not depend on the input, whatever is its present state, that is the output. But in contrast, in a Mealy machine, the output at the present point in time may also depend on the input you are applying. So, present state in combination with the input will give you the output. Now, here again we will be looking at the different design styles that we can use, we can follow, like say for instance, you have the output logic in both cases. Now, it depends on the application. The output logic can be latched, it can be non-latched. Like say for example, you have a circuitry, you have some combination logic. Here you have the primary inputs which are coming, and the primary outputs which are coming out, there can be some latches out there, because there can be some scenarios where the output values need to be kept stable as the inputs change. So, there you possibly need a latch from where the outputs are to be driven. So, there are different design styles. We will be having the memory elements out here. So, they will be driving the memory elements back to here. So, the different design styles we will be looking at, so that the output logic, either in case of the Moore machine or in case of the Mealy machine, they remain consistent and they may be latched or non-latched, it depends on the situation. This means all these things we will be discussing in the next lecture with the help of some example. We will possibly take an example of a simple FSM like a sequence detector, and using the example you can see that how we can model it using Moore machine or Mealy machine, and see that how we can synthesize it. And after that, after looking at the synthesis of FSM, we will talk about some good design styles, or what to do and what not to do. Synthesizable and non-synthesizable. When your target is for synthesis, what are the language features you should limit yourselves to, and what are the things you should not use. There are some rules and guidelines, and in fact, as I told you, these rules and guidelines, there are separate such rules and guidelines from means each and every vendor. There is nothing consistent, but broadly some of the things are common, but there are a few things which may vary across different synthesis tools. So, here all these things we will discuss in the next class. Thank you.